friends, and welcome to Sleepy Time Tales, a podcast aimed at helping you to get a good night's sleep. Do you find your mind plagued with the stresses of modern life, especially when the lights are out and you're trying to get a restful night? Does your spinning mind keep you awake? Follow my voice down the path towards a good night's rest. Listen to me tell a story that will keep your mind from wandering to your daytime problems, the ones you can't solve right now, and will be easier to solve well rested. Listen to my voice and allow yourself to drift, following the twists and turns of the story, but slowly letting go and drifting into sleep. Before we get on with the show, I'd like to ask for a bit of support. If you'd like to support Sleepy Time Tales, to help me keep it ad-free and going out to thousands of insomniacs just like you, please consider supporting it on Patreon at patreon.com/sleepytimetales. This is a monthly support that not only helps me keep the lights on, but can also get you fun bonuses based on how much you contribute. From as little as $2 a month, you get weekly access to early release on the main episodes, so you get your fresh sleep aid on a Wednesday instead of a Sunday. And $5 a month gets you a weekly bonus minisode, special edits, and a monthly megasode, which is all the month's releases in one big listen. You also get a shout out for joining, like this week's new patron, Peen, who has joined the Patreon family. Welcome, and thanks for your support. But I understand if monthly seems like a big ask, because times are tough. But you can also make once-off contributions and tips through buymeacoffee.com/sleepytimetales, or the tip jar on the website. I've also got some basic merchandise up on the TeePublic store, which you can reach through the show notes or via the website. Another way to help without actually costing yourself anything is simply to spread the word. You can help me reach new people by telling the people in your life who you know are struggling to sleep about Sleepy Time Tales. And last but not least, a shout out to the music, which is Weeknight and Friends by Kumiku. The music is available on their website at loyaltyfreakmusic.com. And thanks for taking the time. Let's get back to the show. So what exactly is Sleepy Time Tales? What is it for? What is this strange thing, this strange idea, this podcast that you're supposed to fall asleep to? But in the 21st century, lack of sleep is a health crisis, and this is a podcast intended to help those that it can to get a restful night. Do you find yourself lying awake at night, mind spinning and emotions in turmoil with anxieties of 21st century life? Do you wake up in the middle of the night and find yourself not quite able to doze back off at 3 a.m.? I'm here to help. My name is Dave, and I'm your narrator, here to help you into a restful night. Sleepy Time Tales is intended to be used as a distraction to what keeps you awake at night, or sometimes background noise, or simply company. That's why I make these episodes quite long, so that I'm here for you, without any pressure of the end coming. Now, as far as I know, there are a couple of different ways to engage. The primary idea is that it gives you something to focus on, a story or an event that lets you keep your mind on a specific point, to stop it from spinning out into stress and anxieties, to focus just enough not to resist the embrace of a night's sleep when it comes for you. But maybe your needs are a little bit different. Maybe you just need something in the background. These days people like white noise machines, or sometimes the sound of the ocean, or wind in the trees, or the sound of rain, or maybe even sometimes just some boring dude droning on in the background. But whether you're actually paying attention or just have it playing in the background, the important thing is to remember that you can't force sleep. Just keep a light mental grip on the thread of the story and allow it to come for you naturally. Now, obviously, I'm hoping that you're asleep before we get to the end of the episode, but it is important that you don't feel pressurized. Especially if this is your first night, this will probably actually not work. It will probably take a few nights for you to get used to listening to my voice. Maybe my accent is strange to you, maybe one episode just isn't long enough. Or maybe your problem isn't so much going to sleep. Maybe your problem is waking up in the middle of the night. What I recommend, because of what works for me, is to download a whole bunch of episodes, enough to run the whole night through, and then playlist them and let them go. That way, if you wake up in the middle of the night and the stream is running, you can just pop your earbuds back in and go straight back to sleep again. You can even do the same thing if you're one of those people that tends to wake up a little bit before their alarm, whether 30 minutes or 60 minutes. Just do the same, pop the earbuds back in, go back to sleep. And you might wonder, what is the point of that? What good is an extra 30 minutes or 60 minutes of sleep? And I've got to tell you, I don't know what it is, but there's something about allowing the deep relaxation right before the alarm that's satisfying on a whole new level. So you just need to relax, lie back, go along with this. If you're new to the show and prone to late nights lying staring at the ceiling, this will probably seem strange to you. So give it a chance. Because I'm here to work with you, to create a safe space, a cocoon in which you can curl up and allow nature to take its course. So if you're still with me, thank you for staying. If you're already asleep, we'll chat again soon. And of course you aren't hearing me, except maybe in a dream. After a long break, we return tonight to Astronomy, the Science of the Heavenly Bodies, by David P. Todd. Chapter 5, Measuring the Earth, Aristophanes. All told, the Greek philosophers were probably the keenest minds that ever inhabited the planet, and we cannot suppose them so stupid as to reject the doctrine of a spherical Earth. In fact, so certain were they that the Earth's true figure is a sphere, that Aristophanes in the 3rd century BC made the first measure of the dimensions of the terrestrial sphere by a method geometrically exact. At Cyrene in Upper Egypt, the sun at the summer solstice was known to pass through the zenith at noon, whereas at Alexandria, Eratosthenes estimated its distance as 7 degrees from the zenith at the same time. The difference being about a 1/50th of the entire circumference of a meridian, Eratosthenes correctly inferred that the distance between Alexandria and Syene must be 1/50th of the Earth's circumference. So he measured the distance between the two and found it 5,000 stadia. This figured out the size of the Earth with a percentage of error surprisingly small when we consider the rough means with which Eratosthenes measured the sun's zenith distance and the distance between the two stations. Greatest of all the Greek astronomers, and one of the greatest in the history of the science, was Hipparchus, who had an observatory in Rhodes in the middle of the 2nd century BC. His activities covered every department of astronomy. He made extensive series of observations which he diligently compared with those handed down to him by the earlier astronomers, especially Aristillus and Timacharis. This enabled him to ascertain the motion of the equinoctial points, and his value of the constant of precession of the equinoxes is exceedingly accurate for a first determination. In 134 BC, a new star blazed out in the constellation Scorpio, and this set Hipparchus at work on a catalogue of the brightest stars of the firmament, a monumental work of true scientific conception, because it would enable the astronomers of future generations to ascertain what changes, if any, were taking place in the stellar universe. There were 1,080 stars in his catalogue, and he referred to their positions to the ecliptic and the equinoxes. Also, he originated the present system of stellar magnitudes or orders of brightness, and his catalogue was in use as a standard for many centuries. Hipparchus was a great mathematician as well, and he devoted himself to the improvement of the method of applying numerical calculations to geometrical figures, trigonometry, both plane and spherical, that is, and by some authorities he is regarded as the inventor of original methods in trigonometry. The system of spheres of Eudoxus did not satisfy him, so he devised a method of representing the paths of the heavenly bodies by perfectly uniform motion in circles. There is slight evidence that Apollonius of Perga may have been the originator of the system, but it was reserved for Hipparchus to work it out in its final form. This enabled him to ascertain the varying length of the seasons, and he fixed the true length of the year as 365 and a quarter days. He had almost equal success in dealing with the irregularities of the moon's motion, although the problem is much more complicated. The distance and size of the moon, by the method of Aristarchus, was improved by him, and he worked out, for the distance of the sun, 1200 radii of the earth, a classic for many centuries. Hipparchus devoted much attention to eclipses of both sun and moon, and we owe to him the first elucidation of the subject of parallax, or the effective difference of position of an observer on the Earth's surface, as affecting the apparent projection of the moon against the sun when a solar eclipse takes place. Whereas an eclipse of the moon is unaffected by parallax, and can be seen at the same time by observers everywhere, no matter what their location on Earth. Indeed, with all that Hipparchus achieved, we need not be surprised that astronomy was regarded as a finished science, and made practically no progress whatsoever for centuries after his time. Then came Claudius Tolemaeus, generally known as Ptolemy, the last great name in Greek astronomy. He lived in Alexandria about the middle of the 2nd century AD, and wrote many minor astronomical and astrological treatises, also works on geography and optics, in the last of which, the atmospheric refraction of rays of light from the heavenly bodies, apparently elevating them towards the zenith, is first dealt with in true form. Chapter 6. Ptolemy and his great book. Ptolemy was an observer of the heavens, though not of the highest order, but he had all the work of his predecessors, best of all Hipparchus, to build upon. Ptolemy's greatest work was the Megal Syntaxis, generally known as the Almagest. It forms a nearly complete compendium of the ancient astronomy, and although it embodies much error, because built on a wrong theory, the Almagest nevertheless is competent to follow the motions of all the bodies in the sky, with a close approach to accuracy, even at the present day. This marvelous work, written at this critical epoch, became as authoritative as the philosophy of Aristotle, and for many centuries it was the last word in the science. The old astrology held full sway, and the Ptolemaic theory of the universe supplied everything necessary. Further progress, indeed, was deemed impossible. The Almagest comprises in all 13 books, the first 2 of which deal with the simpler observations of the celestial sphere, its own motion and the apparent motions of sun, moon, and planets upon it. He discusses, too, the postulates of his system, and exhibits great skill as an original geometer and mathematician. In the 3rd book he takes up the length of the year, and in the 4th book, similarly the moon and length of the month. Here his mathematical powers are at their best, and he made a discovery of an inequality in the moon's motion known as the evection. Book 5 describes the construction and use of the Astrolabe, a combination of graduated circles with which Ptolemy made most of his observations. In the 6th book, he mainly follows Hipparchus in dealing with the eclipses of sun and moon. In the 7th and 8th books, he discusses the motion of the equinox, and embodies a catalogue of 1,028 stars, substantially as in Hipparchus. The 5 remaining books of the Almagest deal with the planetary motions, and are the most important of all Ptolemy's original contributions to astronomy. Ptolemy's fundamental doctrines were that the heavens are spherical in form, all the heavenly motions being in circles. In his view, the Earth too is spherical, and is located at the center of the universe, being only a point, as it were, in comparison. All was founded on the mere appearance, combined with the philosophical notion that the circle being the only perfect curve, all motions of heavenly bodies must take place in Earth-centered circles. For 14 or 15 centuries this false theory persisted, on the authority of Ptolemy and the Almagest, rendering progress towards the development of the true theory impossible. Ptolemy correctly argued that the Earth itself is a sphere that is curved from east to west, and from north to south as well. Clenching his argument as we do today, by the visibility of objects at sea, the lower portions of which are at first concealed from our view by the curved surface of the water which intervenes. To Ptolemy also the Earth is at the center of the celestial sphere, and it has no motion of translation from that point. But his argument fails to prove this. Truth and error indeed are so deftly intermingled that one is led to wonder why the keen intelligence of this great philosopher permitted him to reject the simple doctrine of the Earth's rotation on its axis. But if we reflect that there was then no science of natural philosophy or physics proper, and that the age was wholly undeveloped along the lines of practical mechanics, we shall see why the astronomers of Ptolemy's time and subsequent centuries were content to accept the doctrines of the heavens as formulated by him. When it came to explaining the movements of the wandering stars, or planets as we term them, the Ptolemaic theory was very happy insofar as accuracy was concerned, but very unhappy when it had to account for the actual mechanics of the cosmos and space. Sun and moon were the only bodies that went steadily onward, easterly, whereas all the others, Mercury, Venus, Mars, Jupiter, Saturn, although they moved easterly most of the time, nevertheless would at intervals slow down to stationary points, where for a time they did not move at all, and then actually go backwards to the west or retrograde, then become stationary again, finally resuming their regular onward motion to the east. To help out of this difficulty, the worst possible mechanical scheme was invented, that known as the Epicycle. Each of the 5 planets was supposed to have a fictitious double, which travelled eastward with uniformity, attached to the end of a huge but mechanically impossible bar. The Earth-centered circle in which this travelled round was called the deferent. What this bar was made of, what stresses it would be subject to, or what its size would have to be, in order to keep from breaking, none of these questions seem to have agitated the ancient and medieval astronomers, any more than flat earth astronomy is troubled by the necessity of something to hold up the tortoise that holds up the elephant that holds up the earth. But at the end of this bar is jointed or swiveled another shorter bar, to the revolving end of which is attached the actual planet itself, and the second bar, by swinging around once the end of a primary advancing bar, would account for the backward or retrograde motion of the planet, as seen in the sky. For every new irregularity that was found, in the motion of Mars for instance, a new and additional bar was requisitioned, until interplanetary space was hopelessly filled with revolving bars, each producing one of the epicycles, some large, some small, that were needed to take up the vagaries of the several planets. The Arabic astronomers who kept their science alive through the Middle Ages added epicycle to epicycle, until there was every justification for Milton's verses descriptive of the sphere, with centric and eccentric scribbled o'er, cycle and epicycle, orb and orb. Chapter 7. Astronomy of the Middle Ages. With the fall of Alexandria and the victory of Muhammad throughout the West, and a consequent decline in learning, supremacy in science passed to the east and centered around the caliphs of Baghdad in the 7th and 8th centuries. They were interested in astronomy only as a practical and to them useful science, in adjusting the complicated lunar calendar of the Mohammedans, in ascertaining the true direction of Mecca, which every Mohammedan must know, and in the revival of astronomy, to which the Greeks had not attached any particular significance. Harun al-Rashid ordered the Almagest and many other Greek works translated, of which the modern world would otherwise no doubt never have heard, as the Greek originals are not extant. Splendid observatories were built at Damascus and Baghdad, and fine instruments patterned after Greek models were continuously used in observing. The Arab astronomers, although they had no clocks, were nevertheless so fully impressed with the importance of time that they added extreme value to their observations of eclipses, for example, by setting down the altitudes of sun or stars at the same time. On very important occasions, the records were certified on Earth by a body of barristers and astronomers conjointly, a precedent which fortunately has never been followed. About the middle of the 9th century, the Caliph al-Mamun directed his astronomers to revise the Greek measures of Earth's dimensions, and they had less reverence for the Almagest than existed in later centuries. Indeed, Tabit ben Korra invented and applied to the tables of the Almagest a theoretical fluctuation in the position of the ecliptic, which he called trepidation, which brought sad confusion into astronomical tables for many succeeding centuries. Albertesianus was another Arab prince, whose record in astronomy in the 9th and 10th centuries was perhaps the best. The Ptolemaic values of the precession of the equinoxes and of the obliquity of the ecliptic were improved by new observations, and his excellence as mathematician enabled him to make permanent improvements in the astronomical application of trigonometry. Abul Wafa was the last of the Baghdad astronomers in the latter half of the 10th century, and his great treatise on astronomy, known as the Almagest, is sometimes confused with Ptolemy's work. Following him was Ibn Yunus of Cairo, whose labors culminated in the famous Hakamite tables, which became the standard in mathematical and astronomical computations for several centuries. Mohammedan astronomy thrived too, in Spain and northern Africa. Arzakal of Toledo published the Toledan tables, and his pupils made improvements in instruments and the methods of calculation. The Giralda was built by the Moors in Seville in 1196, the first astronomical observatory on the continent of Europe. But within the next half-century, both Seville and Cordova became Christian again, and Arab astronomy was at an end. Through many centuries, however, the science had been kept alive, even if no great original advances had been achieved, and Arab activities have modified our language very materially, adding many such words as almanac, zenith, and radii, and a wealth of star names as Aldebaran, Rigel, Betelgeuse, Vega, and so on. Meanwhile, other schools of astronomy had developed in the East. One at Maraga near the modern Persia, where Nasser Eddin, the astronomer of Hulagu Khan, grandson of the Mongol Emperor Genghis Khan, built and used large and carefully constructed instruments, translated all the Greek treatises on astronomy, and published a laborious work known as the Ilkhanic Tables, based on the Hakamite tables of Ibn Yunus. More important still was the Tartar school of astronomy under Ulugh Beg, a grandson of Tamerlane, who built an observatory at Samarkand in 1420, published new tables of the planets, and made with his excellent instruments the observations for a new catalogue of stars, the first since Hipparchus, the star places being recorded with great precision. The European astronomy of the Middle Ages amounted to very little, besides translation from the Arabic authors into Latin with commentaries. Astronomers under the patronage of Alfonso X of Leon and Castile published in 1252 the Alphonsine Tables, which superseded the Toledan Tables and were accepted everywhere throughout Europe. Alfonso published also the Libretos del Saber, perhaps the first of all the astronomical encyclopedias, in which is said to occur the earliest diagram presenting a planetary orbit as an ellipse, Mercury's supposed path around the Earth as a center. Purbeck of Vienna, about the middle of the 15th century, began his Epitome of Astronomy, based on the Almagest of Ptolemy, which was finished by his collaborator, Regiomontanus, who was an expert in mathematics and published a treatise on trigonometry with the first table of sines, calculated for every minute, from 0 to 90 degrees, a most helpful contribution to theoretical astronomy. Regiomontanus had a very picturesque career, finally taking up his residence in Nuremberg, where a wealthy citizen named Walter became his patron, pupil, and collaborator. The artisans of the city were set at work on astronomical instruments of the greatest accuracy, and the comet of 1472 was the first to be observed and studied in a true scientific fashion. Regiomontanus was very progressive, and the invention of the new art of printing gave him an opportunity to publish Purbeck's treatise, which went through several editions and doubtless had much to do in promoting dissatisfaction with the ancient Ptolemaic system, and was thus most significant in preparing a background for the coming of the new Copernican order. The Nuremberg presses popularized astronomy in other important ways, issuing almanacs, the first precursor of our astronomical ephemeриdes. Regiomontanus was practical as well, and invented a new method of getting a ship's position at sea, with tables so accurate that they superseded all the others in the great voyages of discovery. And it is probable they were employed by Columbus in his discovery of the American continent. Regiomontanus had died several years earlier, in 1475 at Rome, where he had gone by invitation of the Pope to effect a reformation in the calendar. He was only 40, and his patron Walter kept on with excellent observations, the first probably to be corrected for the effect of atmospheric refraction, though its influence had been known since Ptolemy. The Nuremberg school lasted for nearly 2 centuries. Nearly contemporary with Regiomontanus were Fracastoro and Peter Appian, whose original observations on comets are worthy of mention, because they first noticed that the tails of these bodies always point away from the sun. Leonardo da Vinci was the first to give the true explanation of earthshine on the moon, and similarly the moon illumination of the earth, and this no doubt had great weight in disposing of the popular notion of an essential difference of nature between the earth and celestial bodies, all of which helped to prepare the way for Copernicus and the great revolution in astronomical thought. Chapter 8. Copernicus and the New Era. Throughout the Middle Ages, the progress of astronomy was held back by a combination of untoward circumstances. A prolonged reaction from the heights attained by the Greek philosophers was to be expected. The uprising of the Mohammedan world and the conquerors in the East did not produce conditions favorable to the origin and development of great ideas. At the birth of Copernicus, however, in 1473, the time was ripening for fundamental changes from the ancient system, the error of which had helped to hold back the development of the science for centuries. The 15th century was most fruitful in a general quickening of intelligence. The invention of printing had much to do with this, as it spread a knowledge of the Greek writers and led to conflict of authorities. Even Aristotle and Ptolemy were not entirely in harmony, yet each was held inviolate. It was the age of the Reformation too, and near the end of the century, the discovery of America exerted a powerful stimulus in the advance of thought. Copernicus searched the works of the ancient writers and philosophers, and embodied in this new order as such of their ideas as commended themselves in the elaboration of his own system. Pythagoras alone in his philosophy looked in the true direction. Many believe that he taught the sun, not the earth, is at the center of our solar system. But his views were mingled with the speculative philosophy of the Greeks, and none of his writings, barring a few meager fragments, have come down to our modern age. To many philosophers, through all these long centuries, the true theory of the celestial motions must have been obvious. But their views were not formulated, nor have they been preserved in writing. So the fact remains that Copernicus alone first proved the truth of the system which is recognized today. This he did in his great treatise entitled De Revolutionibus Orbium Celestium, the first printed copy of which was dramatically delivered to him on his deathbed in May 1543. The 70 years of his life were largely devoted to the preparation of this work, which necessitated many observations, as well as intricate calculations based upon them. Being a canon in the church, he naturally hesitated about publishing his revolutionary views, his friend Rheticus first doing this for him in outline in 1540. So simple are the great principles that they may be embodied in very few words. What appears to us as the daily revolution of the heavens is not a real motion, but only an apparent one. That is, the heavens are at rest, while the earth itself is in motion, turning round an axis which passes through its center. And the second proposition is that the earth is simply one of the 6 known planets, and they will revolve around the sun as the true center. The solar system, therefore, is heliocentric, or sun-centered, not geocentric or earth-centered, as taught by the Ptolemaic theory. Copernicus demonstrates clearly how a system explains the retrograde motion of the planets and their stationary points, no matter whether they are within the orbit of the Earth, as Mercury and Venus, or outside of it, as Mars, Jupiter, and Saturn. His system provides also the means of ascertaining with accuracy the proportions of the solar system, or the relative distances of the planets from the Sun and from each other. In this respect also, his system possessed a vast advantage over that of Ptolemy, and the planetary distances, which Copernicus computed, are very close to approximations to the measures of the present day. Reinhold revised the calculations of Copernicus, and prepared the Tabulae Prutenicae, based on De Revolutionibus, which proved far superior to the Alphonsine tables, and were only supplanted by the Rudolphine tables of Kepler. On the whole, we may regard the life work of Copernicus as fundamentally the most significant in the history and progress of astronomy. Chapter 9. Tycho, the Great Observer. Clear as Copernicus had made the demonstration of the truth of his new system, it nevertheless failed of immediate and universal acceptance. The Ptolemaic system was too strongly entrenched, and the motions of all the bodies in the sky were too well represented by it. Accurate observations were greatly needed, and the Landgrave William IV of Hesse built the Castle Observatory, which made a new catalogue of stars and introduced the use of clocks to carry on the time as measured by the uniform motion of the celestial sphere. 3 years after the death of Copernicus, Tycho Brahe was born, and when he was 30, the King of Denmark built for him the famous observatory of Uraniborg, where the great astronomer passed nearly a quarter of a century and critically observing the positions of the stars and planets. Tycho was celebrated as a designer and constructor of new types of astronomical instruments, and he printed a large volume of these designs which form the basis of many in use at the present day. Unfortunately for the genius of Tycho and the significance of his work, the invention of the telescope had not yet been made, so that his observations had not the modern degree of accuracy. Nevertheless, they were destined to play a most important part in the progress of astronomy. Tycho was sadly in error at his rejection of the Copernican system, although his reasons in his day seemed unanswerable. If the outer planets were displaced among the stars by the annual motion of the Earth around the Sun, he argued, then the fixed stars must be similarly displaced, unless indeed they be at such vast distances that their motions would be too slight to be visible. Of course, we know now that this is really true, and that no instruments that Tycho was able to build could possibly have detected the motions, the effects of which we now recognize in the case of the nearer fixed stars, in their annual or parallactic orbits. The remarkably accurate instruments devised by Tycho Brahe and employed by him in improving the observations of the positions of the heavenly bodies were no doubt built after descriptions of astrolabes such as Hipparchus used, as described by Ptolemy. In his Astronomy Instaurate Mechanica, we find illustrations and descriptions of many of them. One is a polar astrolabe, mounted somewhat as a modern equatorial telescope is, and the meridian circle is adjustable so that it can be used in any place, no matter what its latitude might be. There is also a graduated equatorial ring at right angles to the polar axis, so that the astrolabe could be used for making observations outside the meridian as well as on it. This equatorial circle slides through grooves and is furnished with movable sights, and a plumb line from the zenith, or highest point of the meridian circle, makes it possible to give the necessary adjustments in the vertical. Screws for adjustment at the bottom are provided, just as in our modern instruments, and 2 observers were necessary, taking their sights simultaneously, unless, as in one type of instrument, a clock or some sort of measure of time was employed. Another early type of instrument is called by Tycho the Ecliptic astrolabe. It resembles the equatorial astrolabe somewhat, but is a second ring inclined to the equatorial one at an angle equal to the obliquity of the ecliptic. In observing, the equatorial ring was revolved round, till the ecliptic ring came into coincidence with the plane of the ecliptic in the sky. Then the observation of a star's longitude and latitude, as referred to the ecliptic plane, could be made, quite as well as that of right ascension and declination on the equatorial plane. But it was necessary to work quickly, as the adjustment on the ecliptic would soon disappear and have to be renewed. Tycho is often called the father of the science of astronomical observation, because of the improvements in design and construction of the instruments he used. His largest instrument was a mural quadrant, a quarter circle of copper, turning parallel to the north and south face of a wall, its axis turning on a bearing fixed in the wall. The radius of this quadrant was 9 feet, and was graduated or divided so as to read the very small angle of 10 seconds of arc, an extraordinary degree of precision for his day. Tycho built also a very large alt-azimuth quadrant of 6 feet radius. Its operation was very much as if its mural quadrant could be swung around in azimuth. At several of the great observatories of the present day, as Greenwich and Washington, there are instruments of a similar type, but much more accurate, because the mechanical work in brass and steel is executed by tools that are essentially perfect. And besides this, the power of the telescope is superadded to give absolute direction, or pointing on the object under observation. Excellent clocks are necessary for precise observation, with such an instrument, but neither Tycho Brahe nor Hevelius was provided with such accessories. Hevelius did not avail himself of the telescope as an aid to precision of observation, claiming that pinhole sights gave him more accurate results. It was a dispute concerning this question that Halley was sent over from London to Danzig to arbitrate. There could be but one way to decide. The telescope with its added power magnifies any displacement of the instrument, and thereby enables the observer to point his instrument more exactly, so he can detect smaller errors and differences of direction than he can without it. And what is of great importance in more modern astronomy, the telescope makes it possible to observe accurately the position of objects so faint that they are wholly invisible to the naked eye. And I think I'm going to leave it there. As always, if you'd like to pick up where we've left off, you can find Astronomy, the Science of the Heavenly Bodies, on Project Gutenberg at the link in the show notes. Thanks again for joining me on this episode of Sleepy Time Tales, the podcast designed around a bedtime story to help you to get a restful night. New episodes are released every Sunday night to give you something fresh to help you rest in a new week. But make sure to subscribe in whatever service you use so that you get your new episodes whenever they come out. A reminder that the music for tonight is Weeknight and Friends by Kumiku. Check out more of their work on their website, which you'll find linked in the show notes. Good night, and sweet dreams.